Now we want to define the notion of submanifolds of a smooth manifold M. We want to use a more modern viewpoint, so we don't need the submanifold to actually be a subset of M. Rather, it could be another manifold equipped with a map to M. We say that a manifold N is an immersed submanifold of M if there is a one-to-one immersion from N to M. Or equivalently, people also identify this N with its image in M. So we might say an immersed submanifold is a subset of M that is the image of a one-to-one immersion, but with the topology inherited from this N via F. Right, so we identify this with N. This F is naturally a homeomorphism if we define the topology here to be induced by it. Now observe though that this topology that we just said, the topology of this induced from F, it does not necessarily have to be a subspace topology of M. If this image Fn with the subspace topology, not this induced topology, if this image Fn with the subspace topology is actually homeomorphic to N under this map, then we call Fn an embedded submanifold. So in terms of map, we can think of an embedded submanifold as also a one-to-one immersion, but with the additional condition that is a homeomorphism onto its image, where its image is equipped with a subspace topology. It turns out that all embedded submanifolds are regular submanifolds, i.e. they are locally cut out by coordinate functions. But we'll discuss that a bit later. For now, let's look at some examples. Let's first look at these two examples of maps from R to R2 to see why we would require the manifolds to correspond to one-to-one immersion at minimum. Well, let's have a look here. We have an injection into R2, but this doesn't look like a manifold, right? And the problem there is that this tangent space here, well, the differential of this map, so the map on tangent space at the origin, sends this whole tangent space here to 0, so it's no longer injective, means it's not an immersion. And that introduces a sharp corner, and that's bad, so it doesn't look like a manifold, so we want to rule out this case. But just being immersion, it's not enough, because this map, for example, is an immersion, the map on tangent space is injective, but this map is not one-to-one. And a manifold cannot have a crossing like this. So we also want to rule out cases of maps that are not one-to-one. Thus we define immersed submanifolds to be one-to-one immersion of a smooth manifold into M. Now here we want to make two remarks with regards to immersed submanifold. The first one is that two immersed submanifolds might have the same image, but they are still distinct immersed submanifolds because they are image of different maps. Or in other words, the manifold structure on the image might be different. For example, the figure 8 is an immersed submanifold of M, but the immersed submanifold structure can be chosen in many ways. So that could come from the manifold structure on this interval via this map, or it could come via this map, and that's going to be a very different structure. And now to the second remark, which really introduces us to embedded manifold, which is observe that even though we've added the condition one-to-one and immersion to prevent ugly things, pathologies from happening, we see that these are one-to-one immersions, but the image still do not look at all like a manifold. It's a manifold with respect to the topology inherited from here, but not with respect to the subspace topology. An open set on figure 8 around the origin must be the intersection of an open set of R2 with figure 8, and that does not look like an open set in Euclidean space. Thus, we want to add the condition that F is a homeomorphism onto Fn with subspace topology, and then in that case we have the notion of an embedded manifold. Recall previously we have examples of maps that are not immersed submanifold. Now let's look at these maps from R into R2, mapping this, wrapping this line here, or here is mapping to the topologist's assigned curve here, but we connect this point. So these are immersed submanifold, but they are not regular submanifold because they are immersion and they're one-to-one. But under the subspace topology, these aren't manifold. They are not homeomorphism from R into this image under the subspace topology. For example, here an open set around P in the subspace topology would contain this whole thing here, and that doesn't look like R. Before moving on to talk about the nicer embedded submanifolds, we want to address a question. So you're probably going to ask, why would we even care about immersed submanifolds at all then? Why not just work with embedded submanifolds? Well, so let us give you an example where this notion of immersed submanifold might be useful. For example, if we have a Lie group and then let's call this corresponding Lie algebra, we will have a bijection. We want to have a bijection between connected Lie subgroups and Lie subalgebra, connected Lie subgroups of this big G and Lie subalgebra of this little g. And we will not have a bijection. We will not have enough subgroup. We will not have enough bijection if we only allow the Lie subgroups to be embedded submanifold and not immersed submanifold. For example, let's look at the case when the Lie group is the torus, so it's the quotient of the plane by a lattice. Right, so in that case, the one-dimensional Lie subalgebras are just going to be lines through the origin in the plane. And here are the image on the torus if we take this quotient by this square. Now observe that this line is a regular submanifold if and only if it has rational slope. Those with irrational slope will not form a regular submanifold. They actually will have a dense image in here. So if we do not allow immersed submanifolds, then those lines, those subalgebra, Lie subalgebra, those lines with irrational slope will not have a corresponding connected Lie subgroup. And that's why we want to extend the concept of submanifolds to also immersed submanifolds. Next, we want to address another characterization of embedded submanifolds. They are the same as another class of submanifolds called regular submanifolds.